So we're aiming for 3 minutes.
Yeah.
5 minutes.
Yeah.
15. Okay, everybody. I apparently am chairing this session, which I'm not certain that was originally the plan, but now I am. I'm Phil Mote, and I'm pleased to introduce Ann Nolin, who's the first of our speakers in this session. So take it away, Ann.
Thanks, Phil. Okay, so I want to start, before I jump into my talk, I want to give you a little bit of a news update. Kathy Dello and I are going to be the conveners of next year's Pacific Northwest Climate Science Conference. Woo-hoo! Yay! And it's going to be in Portland. Yay! And so please save the date. It's going to be sometime the week of October 11th to the 14th for 3 days, sometime in that week. We haven't firmed up the exact 3 days, but in that period it'll be either the 11th, 12th, and 13th, or the 12th, 13th, and the 14th at the Sentinel Hotel, and you'll be hearing more about it pretty soon. So it's still almost a year away, loads of time, but just wanted to give you that announcement. Kathy's going to be making a more formal announcement tomorrow, but I'm leaving later today, so. Anyways, I do want to say, though, that this is all new work and very, very early days with this. So we got an NSF Rapid grant to measure stream flow on the heels of this record low snow year. And so I'm going to be talking about our hypotheses and our findings and our early synthesis in this regard. Okay, so these are some data from one of the SNOTEL sites in the region where we've been working in the Oregon Cascades. This is the Mackenzie SNOTEL site. And as you can see, as has been indicated by a lot of speakers earlier today, that so gosh, I don't know if this is a laser pointer or not. It's not clear to me. Sorry, pause for a moment. The yellow line is 2014, the red line is 2015, and the black line is the median precipitation over a 30-year period, and the gray areas are the full range of the data. So you can see that the snow is extremely low here. So that was precipitation, my apologies. That was precipitation. So near normal precipitation, actually a little bit higher than normal for 2014. Wintertime goes up to here. This is precip right here for winter. It was just spot on normal, and then it dropped off. We had a really dry spring. Here's the snow. The 2015 snowpack just really fell off the charts. And again, not because it was dry, but it was because it was very, very warm. How warm? In this area, between 3 and 4 degrees Celsius warmer than normal. So here is our study area. The whole Columbia River Basin is of interest to us, but we're really working here at the crest of the Cascades in the headwaters of the Mackenzie River Basin, and not shown the headwaters of the Deschutes River Basin, the upper Deschutes. So we see this as not just a drought, but a research opportunity. So our main research question is, how do headwater streams respond to this low flow regime, this low snowpack that we have? And how is this low recharge then affecting late summer stream flow? So we're really interested in the lowest stream flows of the year. And then there's also a geomorphological part of this that's related to the hydrogeology of the region, which is the stream network topology. How does that change given changes in flow? And I'll tell you a little bit more about that. So here's a little bit of a finding so far. As the summer progressed, this flow, we got to low, but we never got any lower than previous low flows. Interesting. Why is that? More questions. This has led us to wonder about our hydrogeologic landscape and wonder what does this mean for the future. So our hydrogeologic landscape, we have spring-fed streams, we have surface flow streams, we have end members, that is essentially pure representation of those two types of hydrogeology. And you can see the two different landscapes here. On the top is this almost sort of barren-looking lava landscape, basalt landscape, highly permeable, highly porous, basalt sponge, as it were, with very little river network developed. There's almost no incision there. Here is the Western Cascades, old basalts, very highly basalt in size, big V-shaped, very steep-sided valleys, so a very different type of a network. And so this is surface flow, and up here is the spring-fed. What does that look like in terms of the flow? Well, here on the top is the spring-fed, and that's exemplified by a location we call that's called Clear Lake. And you can see here measurements, the black line, and then modeled data from the RESIS. It's a regional eco-hydrologic simulation system model for plus 1.5 degrees C in the blue for spring-fed, and plus 1.5 degrees C future flows for the surface flow. And you can see different characteristics. So in the spring-fed, we still have flow in the summer, but in the future, in this warmer modeled condition, you have a decrease because there's water that can be removed from the system. In the surface flow system, you always pretty much get to zero, and even if you convert from snow to rain, it's still going to be zero in the summer. So there's very little change in late summer flow in these modeled results. So this is how we think the system would behave, and let's see if it really does. Okay, so here is the second hypothesis, is that surface flow and spring-fed systems, the networks, are going to have different styles of accommodating these decreased flows. So this is the network topology difference. So it might be that in the surface flow system that you just have the length of the entire network decreases. Or it could be that the network length doesn't change. You still have streams occupying all parts of the network, but perhaps they just get narrower. That is, the wetted width of the channel decreases. That has implications for fish and aquatic habitat. Spring-fed, we have also the similar set of hypotheses. One is that maybe the heads of the channels, these spring heads, kind of jump downstream as the upper springs go dry. Or it could be, like in the other case, that the springs just decrease flow and that the wetted width of the channel narrows, but you still have the same length of channel. So in the upper case, in both of these, we would have a longitudinal contraction, that the network gets shorter. You lop off the ends of the channels, or it could be that you have a lateral contraction, that the channels just all get narrower. Our study sites, we've got actually 6 study sites. I'm really just going to tell you about 2, Anderson and Boulder. And so Anderson is spring-fed, as are all of the little areas outlined in blue, and then Boulder is surface flow, as are the headwater catchments that are outlined in green here. We've got 4 that are on the west side of the Cascades and 2 that are on the eastern leeward side of the Cascades, the drier side. Okay, and this is sort of what the system looks like. We've got a series of longitudinal cross sections in which we measured stream channel characteristics and flow and temperature. So we had installed some gauges at all of these sites. So here is Anderson and Boulder. And I just want to point out the difference between the two. Here is this spring-fed system here, and then here's the surface flow. As the recession proceeds during the dry season, you can see the spring-fed system still has loads of water in it, but the surface flow system really has just disconnected pools. Like here's a little pool here, and here's another one down here. Just little puddles of water with trickles of just rivulets through the gravels here. So very little connectivity. This is kind of interesting. This is the Clear Lake set of hydrographs, and let me walk you through the spaghetti diagram. The different colors represent different years, and the years are indicated in the colored boxes. I want to point out a couple. One is 1992, which is this orange right here. Can you see that line right there? Right there? That is really at the very lower part of the envelope. And so the gray represents the full range of flow, and this is summertime. Here's 2015 in red, that dashed line here. That's as far as we got in our measurements there, and then usually in the fall everything gets wetted and jumps right back up again. So here's 2015. It went just as low as 92 and did not go any lower. That was a big surprise to us. And we are wondering why also all of these recession parts of the hydrographs are essentially parallel. Note though that this is a log plot here on this axis, discharge on the y-axis. But it is interesting to us that it's parallel. So essentially they have the same behavior regardless of whether or not you start here and go down, or if you start here and go down. They all seem to have similar recession behavior. I do want to point out that if you look at this quad chart, we've got low rain, high snow, high rain, high snow. So up here, these two quadrants are high snow, down here, low snow, low snow. So low, high rain. So all of the lowest years, which are indicated in red, with the exception of '02, have low snow. But what about the sequencing of drought years? Drought years don't really just happen in isolation. Here's an example, 90, 91, and 92. So it's sort of getting progressively drier as you go to lower snow. And all of them have roughly average precipitation. So this line right here, this vertical line represents average precipitation. This axis right here through the middle represents average snow. Notice this one is kind of interesting, 2013, 2014, and 2015. Again, moving progressively towards lower snow as time goes on. So it'll be really interesting to see what happens with 2016. We don't know. But what we can say is that the stream flows are influenced by how much winter precipitation you get total, rain plus snow, the timing of the last recharge pulse, the low flow from last year, because we're trying to fill up these groundwater buckets, and then the onset of the fall rains as well. So just to give you a little bit of an overview, some of our findings, we see that in the spring-fed system, the summer flow is about 15% lower than it was last year, but it still fills the active channel as shown in that photograph earlier. The surface flow system in Boulder Creek, order of magnitude lower than last year, really low. But we expected that. But what was interesting too is we did find some cold sources, so there is a little bit of a spring component there. It's temperature-wise, it's really cold. So we do see a loss of this longitudinal surface water connectivity, but we didn't see any major contraction, longitudinal contraction of the stream network. So early observations, very little longitudinal contraction, so we don't really see this happening. We see this, that the channels are getting narrower, particularly with these V-shaped channels. Not much happening with the spring-fed rectangular channels. Okay, so I hope I have like a minute to walk you through this. Why are they so different? Well, we think it's because of the shape of the watersheds. Okay, so I'm going to walk over here and point. All right. This is a big V. So here's the edge of the watershed. So you can only put water into this stream from this area, right? And so if you don't have that much snow up here, you're really going to be pretty limited here. Over here on this landscape, there's no edges. There's no boundary to this system. So we really have perhaps an unbounded groundwater system. It's immense. It's a giant sponge. It's probably on the order of something like Lake Mead. So we can use this approximation to the Navier-Stokes equation to think about this, and I don't have time to really go into it, so I'm going to skip that. But I do want to show you, though, that this Clear Lake, when we plot that in this kind of Boussinesque space, what we see in this hydrologic space is that the Clear Lake is always behaving as if it's kind of early days in the recession limb, as if there's always tons of water, because there is. And Lookout Creek, which is a surface-fed system a little bit further down from our Boulder Creek, is always behaving pretty much as if it's late in the game in recession. And so that's kind of the story there, is that we have loads and loads of water in the spring-fed end member systems. So our preliminary results, we expected the record low flows, we didn't get them. The High Cascades Aquifer must be huge. We're not sure what's going to happen here. The age of the water is on the order of maybe 2 to 4 years. So we might start seeing something happening in a couple of years. Well, not sure. I just want to end with this very last slide. This is something that went into publication last week, submitted for review last week. This is exceedance probability of water storage by elevation. For if you have a plus 2 degrees C system scenario, where do 2014 and 2015 fit into that? Well, 2014 is pretty average for a plus 2 degree system. 2015 is still at the really, really far extreme end, even for a plus 2 degree scenario. So with that, I will end and just say it really was an extraordinary year, but surprisingly, it wasn't that extraordinary for the stream flow in the spring-fed system. Thanks.
Time for questions? Yes?
So I'm less familiar with the Oregon network, but Washington State USGS Streamflow Network saw record low flows in like 64% of their gauge sites this year. Do you think there's something different about Oregon's network versus Washington's network?
Well, it's not the measurement devices. It's the fact that what we're doing, so it's not about the place, it's about the hydrogeology. So the fact is that we're using these as exemplars of a spring-fed system and a surface flow system, in which, so you can mix those types of geologies together and get almost anything. So we're using this really to demonstrate the differences between a spring-fed response and a surface flow response in an extreme snow drought year. And so don't think of it as this happens in Oregon. Think of it as it happens in this kind of hydrogeologic setting. So these are end members in a hydrogeologic sense.
So with, this is one particular year, but with climate change, there's going to maybe be continuous stress on the system. Do you see these two systems responding differently in that context?
Yeah, I think that we have a lot to learn about the spring-fed systems. We don't know the volume of water that's available there and the connectivity. So if you imagine like a whole bunch of pools of water under the ground that have some level of connectivity, that if you fill up all these pools, then you have more, maybe a continuous surface that's sloping, along with the topography. But when you start to drop that down, then the connectivity is lost, and some springs are still going, whereas others will turn off. And so over time, I would expect that we would understand more about the hydrogeologic connectivity of the system. So if we have another year of drought, that would actually be terrible, but interesting. So, yeah.
Question, did you measure temperature? Did you see an effect difference between the two systems on temperature response? Meaning, did one get more warmer than historical average?
Right. We have measured temperature. Our preliminary analyses show that they're both pretty cold. We expected the surface flow system to be a lot warmer, and it wasn't. So we think that there's the base flow there is probably fed by springs. So, and we are measuring temperature. Again, we just started this project in July, so it's still pretty new.
One more question.
Really neat study. Just curious how you would identify if there was longitudinal decreases in the stream network.
We hiked it, and
But you didn't hike it in 2014.
no, but we hiked it at the beginning of the recession, and then as the recession proceeded, we could see like every 2 weeks where the furthest source of the water was. So we'd love to do it again. It would be great to do it next year and start earlier. So thank you.
Thanks a lot, Ann.